Welcome, welcome. We'll begin in shortly in about 2 minutes as we get everybody settled. And again, good afternoon, good morning, good evening, wherever you may be. Thank you so much for joining us today. Thank you so much. We have about a minute to go before we get started, so I just wanted to give everybody an opportunity to get into their virtual space and get settled in. And thank you so much for coming. We're excited to have y'all. And at this time, just a quick housekeeping note. If you have a question, please place it into the Q&A feature at the lower bottom of your screen versus the chat. And if we have time, we will go through as many questions as possible, and we will continue to engage with our speaker and others post the event should time allow. So at this time, I would like to turn it over to our chief scientist, Dr. Roach. Over to you, sir.
Andy, thank you very much for as usual, setting this all up and allowing us to have the Chief Scientist Distinguished Lecture Series. I'm not going to steal any of Dr. Stickrath's thunder when he introduces our speaker today, but I do have to acknowledge the fact that I've known Professor Milchberg since around 2010, 2011, and worked with him very closely. And I'm happy also to say that I call Howard a friend. He's been a great colleague and in many cases a great mentor on things we were trying to do when I was at Kirtland Air Force Base and beyond. So he has a lot to say. He's been in this field for quite some time, and he's been considered one of the leaders and fathers in a lot of the area of the development of what femtosecond lasers could do. I also want to say to everyone that this is our 15th Chief Scientist Distinguished Lecture since we began. Our paradigm here is a little different in that we ask academics at the height of their profession to join us to talk to us about what's happening literally globally in terms of scientific discovery and what's uppermost in their minds in terms of what the future looks like for basic science and discovery as we go forward. But with that, I'd like to turn it over to Dr. Stickrath, who's the program manager for our femtosecond portfolio here at the Air Force Office of Scientific Research. Andy, over to you, sir.
Thank you, Pat. So good afternoon, everyone. Thank you for joining this installment of the AFOSR Chief Scientist Distinguished Lecture Series. It is my distinct honor to introduce Howard Milchberg. He is a professor in the departments of physics and electrical and computer engineering at the University of Maryland. And his widely interdisciplinary research and high-intensity laser physics spans the fields of plasma and high-energy density physics, advanced particle accelerators and light sources, atomic physics, nonlinear optics, and structured light. In fact, actually, I didn't realize, I just learned when I looked at his bio here that his PhD from Princeton was actually awarded in astrophysical sciences. So Professor Milchberg has received many honors. I'll just highlight two of them today. One, I think, is an important one, and that is that, well, they're all important ones, but one important one is that 3 of his graduate students have received the American Physical Society's Division of Plasma Physics Outstanding Doctoral Thesis Award. I think that really says a lot. And another thing I'd like to recognize is that Howard will be recognized with the 2024 Arthur L. Shallow Prize for Laser Science. The citation for that award reads, "For pioneering contributions in the fields of plasma optics, guiding ultra-intense laser beams, and developing compact, high-gradient laser-driven accelerators." And I would just add that I think, Howard has really helped to introduce a rigor in precision to the field of to high-field laser science. So today he's going to tell us about another exciting direction in his research, and that is focused on intense femtosecond pulse propagation and structured light. So Howard, the floor is yours.
Okay, well, thank you very much, Pat and Andy, for inviting me to give this colloquium. It's a great honor, and thank you, Andy, for that very nice introduction. So today I'm going to talk about something that we got into because we had the diagnostics that we developed for some of our intense plasma physics work with application to advanced acceleration driven by lasers. So we had these ultra-fast diagnostics, and we decided to turn them toward understanding intense femtosecond pulse propagation in air. And so a lot of the work you see here has been funded by the folks listed here with their logos. And this work couldn't have been done without the fantastic graduate students and postdocs at the University of Maryland. The ones with the asterisks are still around. Andrew Goffin hasn't graduated yet. Scott did just graduate, and he is a current postdoc. And the rest of the folks here are at national labs, DoD labs, and industry. And also over the years, we've had excellent collaborators. Longtime collaborator at Maryland was Tom Antonsen, a theorist at Arizona, Miro Kolesic, Jorge Roca. We've done some experiments with recently, and in fact, some of my students are at Colorado State University right now doing a laser wake field acceleration experiment. Eric, listed in both lists, he's a former student and he's now at NRL, and he's continued to collaborate with us. Tony Valenzuela and Aaron Schweinsberg at ARL, and a couple of experiments with the group of Jean-Pierre Wolf at Geneva. Okay, so we got interested in ultra short femtosecond pulse propagation in gases. Why did we get interested? Well, it wasn't just we were interested and could do nothing about it. We had these interesting ultra-fast diagnostics to look at the physics, and I'll talk about those as the talk develops. And let me also say at this point that once that interest was developed, and once we started getting into this thing, we followed our noses, and so during this talk you're just going to hear how one thing led to another, and by the end of the talk, some of the material may be somewhat hard to understand and a little weird, but it's basically what following our noses has led to. So you'll see that. So basically, and I'm sorry if some of this is too elementary. I know the group attending today is quite diverse in background. So some of this stuff may be a little elementary, but I'm going to just go over it quickly. So with a CW or a weak laser pulse propagating through vacuum or air, basically the beam diverges because light is a wave, and the Rayleigh range is just the distance over which the beam intensity drops by a factor of 2. You use a lens, the same wave physics applies, except the Rayleigh range is just shorter. Same kind of thing, intensity drops by 2. So 2Z naught is the confocal parameter. Something really interesting happens, and we knew about this before we got into it, but if you take a millijoule pulse, which is about 100 femtoseconds in duration, and this experiment was done for the first time, at least maybe it wasn't the first time, but it was the first time they paid attention to it and did measurements, was with Gerard Maroux's group at the time at Michigan. And they published an optics letter in 1995 that has a huge number of citations now. They found when they sent the pulse out of the laser and let it propagate through room air, at some point it just collapsed, and then it propagated as a thin laser plasma filament. So the beam went down to a very narrow diameter. Typical diameter is a couple of 100 microns or less. And it generated a white light beam projected in the forward direction, and the beam was sort of centered in this outside region called a reservoir. So the thing in the center is called the core, the thing on the outside is the reservoir, and so here this thing is. This was very intriguing to us. We got into trying to work in this area maybe 10, 12 years later. So a lot of this stuff was out there. There were a lot of publications in this area. And basically, worldwide people were sending 100 femtosecond lasers, millijoules, few millijoules across rooms and doing experiments with them. One of the early ideas is, well, because you're making a plasma in this filament, could you use that as a conducting wire? Maybe that's an application. Maybe you could just discharge high voltage capacitors using this, or to make or guide lightning with this. So one of the issues is the electron density is on the low side. It's less than 10 to the 17 per cubic centimeter, even less than 10 to the 16, which is well below 0.1% of atmospheric density. So it's low. So just as a very quick review, how do you make these short pulses that you propagate through air, 100 femtosecond, and then they collapse? Well, the Nobel Prize was awarded in 2018 for this. And this is basically the scheme here. Send a short pulse in, and then you stretch it and you amplify it, and then you recompress it. And you do that so that you don't destroy the amplifiers for exactly the same reason that a pulse collapses in air. A pulse will collapse in any material medium. The threshold for doing this in a solid amplifier is much lower. So one reduces the peak power by stretching. So that's the basic scheme. And there are two kinds of regimes among the regimes our group works in. One is very high power. In fact, these are the characteristics approximately of the laser at Colorado State University, where my students are now, several of my students are still working on the wake field acceleration. And the talk today is about millijoule type pulses, not 10 joule pulses, millijoule type pulses, 50 femtoseconds. Focused intensity is 10 to the 13 or greater. So just to give you a sense of what we mean by 50 femtoseconds, I mean, here's two sort of limits in that realm. One is the orbital time of an electron around an atom. That's about a femtosecond. And in fact, this is why attoseconds are so interesting. If you want to do these kinds of time-resolved experiments and learn things on an atomic orbital scale, you want to be below a femtosecond or in the attosecond regime. So femtosecond is about that time scale, orbital time. And then in condensed matter, the vibrational time scale is about 100 femtoseconds. So what are filaments good for? Well, one thing is directed intensity, as indicated. You know, the filament core could have 10 to the 13, 10 to the 14 watts per square centimeter in it. But directed energy, not clear, because it's just a few millijoules in this core, and the core isn't the whole beam energy. Triggering and guiding of electrical discharges, this has been demonstrated. In fact, I'll show in the next slide about the guiding of lightning. But the issue here is that it's not due to the electron density of the plasma filament. It's more due to the air heating and the reduction of air density. So there's a discharge channel that's formed. I'll talk about that later in the context of additional work we did. Remote lasing of air molecules, I put a question mark because there's a range of experiments. It's not clear that it can be done usefully in the air yet. Remote detection, yes, these depend on peak intensity. So these are things that can be done. Terahertz generation, high harmonic generation, supercontinuum generation is done routinely in labs using filamentation. And the supercontinuum is coherent and it's usable for other experiments. One element of the talk today will be to show how filaments can be used to guide high average power beams. The filaments themselves are not high average power, but they can enable the guiding of high average power beams. I'll talk about that. And then the point I want to make today is that this sort of curiosity to us at the beginning is filled with fun, rich physics. And I hope to convince you that our journey through this area was interesting and rewarding. So here are some examples of filament applications. One was basically LiDAR over a kilometer, multiple kilometer scales. This was an experiment done in 2003. So it's the supercontinuum basically is backscattered and collected in this case with a giant mirror. And the other point is, and it's still in the same paper, they show that you can guide high voltage discharges using these filaments. So there's a laser filament propagating from left to right in this picture. At the time, they thought it was due to air conductivity increasing because of the plasma, but in fact, it's because of the air density reduction, because the filament heats the air and the electron density is gone, long gone by the time the discharge happens. And then most recently, and this got a lot of press last summer, on a mountain in the Alps, they have a kilohertz laser by Trumpf that is aimed just past the lightning rod on this structure here. And so here's an example of sort of random lightning encountering the laser beam and then being guided down to the lightning rod. So this is approximately 50 meters. They got several shots that showed this effect. Again, it's not from the plasma in the filament largely, it's mainly due to the electron density, or excuse me, the gas density reduction in this channel caused by the filamentation. In our lab, filaments are used for supercontinuum generation, which we use in a diagnostic that I'll talk about, but we have a xenon-filled tube, a couple of atmospheres, and a femtosecond beam of order a few hundred microjoules is launched from the right here, and it filaments. And as I showed in an earlier slide, you get a white light beam in the forward direction. And here it is. Here's the spectrum with the background filtered away. So it's quite a broad, coherent spectrum. So in terms of the physics, it's of interest to think about where filaments live in parameter space. Here's a plot that many of you are familiar with, which shows the evolution of laser power versus year. So in the bottom left corner, there's the Ruby laser from 1960. And then many of you are familiar with these different developments, Q switching, mode locking, and then this big step up here, jerk pulse amplification. And you know, it's arguable, you could sort of move some of these boundaries around here. The point for filaments, though, is that they live in between bound electrons and free electrons. In fact, because the electron density is about 10 to the 17 or less, and that means the ionization fraction in air is about 0.1%. Most of the molecules and atoms in air are not ionized, they're neutral, and they're sitting in a very low density plasma. And the laser field is non-perturbative because it is capable of ionizing the molecules. So filaments are living in this very interesting location where the electrons are exposed to non-perturbative fields. So just to start with, again, a simple model, because we're talking about nonlinear interaction. So here's an atom in a laser field, small electric field. You turn on the field, you stretch the atom, and if we imagine the atom to be an electron attached to the nucleus by a spring, you can sort of draw this plot and say, well, pre-1960, pre-Myman, you know, we were in this linear area. The spring stretch was linear in the electric field, and after that, we had enough field strength to cause nonlinear response. And once we have a nonlinear response, we can say, well, we can do perturbation theory, and we can expand the nonlinear polarization of the atom in terms of powers of the electric field. And we can say, well, let's impose symmetry so that a plus field and a minus field, you know, there is a sign effect here, so we have to get rid of that, because plus causes a plus polarization and minus causes a minus polarization. So by symmetry, we get rid of that. And then we can group terms. So we have this thing that's a lot like a susceptibility times an electric field, which we can then write down as an effective index. So effective index squared is, in Gaussian units, 1 + 4 pi times this effective susceptibility. And then that allows us to calculate an index. So this is an index of refraction, which has this unperturbed part, which is just N naught, the boring regular air index, and then a second term, which is proportional to the square of the electric field. This N2 is the so-called nonlinear index of refraction. Now, why am I talking about perturbation theory when I just said in the previous slide, we're not in perturbative regime? It's because, and this is one of the things I'm not going to get into in this talk, but if you're interested, you can check out this paper. And I have a bibliography that I can distribute after the talk with all the things that we've done over the years. But this is a paper that actually shows that this expression is actually still good in the non-perturbative regime. And we did measurements of N2 for that case. So that's an interesting paper you may want to look at. And in fact, many high field propagation models for filaments use this expression. So what effect does that thing have? So here's a regular laser pulse. It's just low intensity, let's say. The intensity is proportional to the square of the electric field, and here are the phase fronts. Now, if we dial up the intensity, we have an effective index of refraction, which has a bump due to the second term here. So here it is. The second term causes a bump in the index of refraction, which then slows down the phase fronts at the center of the beam. So flat set of phase fronts becomes a converging set of phase fronts, and that causes self-focusing. And the threshold for that happening is typically 10 megawatt in solids. This is why you have to go to chirp pulse amplification, because if you don't do that, this threshold for focusing will cause damage, and tens of gigawatts in gases. And this is basically a factor of 1,000 different because of the factor of 1,000 difference in density between solids and gases. So this thing self-focuses, and it would go to a singularity, because as it self-focuses, it gets more intense. This index bump goes up, it causes stronger self-focusing, and it would run away and ionize the medium. In fact, that's what saves you, because once it ionizes the medium, this electron density from ionization turns into a negative lens. So here is, let's say, a simple model of ionization. It's just a perturbation theory model, with K being the number of photons to ionize, and it just serves the need for a nonlinear model in this case. So the details of the model aren't important, but it's strongly peaked on beam axis. Notice here that the electron density in the index of refraction provides a negative increment. This means that free electrons are negatively polarizable. So now you actually have the index going the other way. The effective bump in the index is due to this negative sign. It goes the other way, and that causes the phase fronts to defocus. So the phase fronts are bumping the other way. So this is what actually causes the arrest or the stopping of this tendency to go to a singularity. So it's self-focusing collapse arrest. It's affected by ionization. So the simple model of filamentation is this. It's a static model, and it just says that you're going to get collapse first when self-focusing beats diffraction. Okay, when diffraction is no longer something that causes your beam to diverge, because self-focusing is beating it, the beam collapses. It gets to an intensity level where it ionizes the air or whatever gas you have there. That makes a plasma with a negative index bump. Okay, the gas has a positive index bump because of the self-focusing, and diffraction causes beam divergence, and it has an effective negative index bump. When all of these things sort of add up and they're zero, then you have this thing propagating like this. So this is a very simplistic steady state model. It's not at all what happens. It's actually a very dynamic process, but it was our curiosity about this that led us to do further experiments. Here are some pictures of filaments, its characteristics. So when you're below the critical density for this self-focusing, again, the critical power is when the self-focusing inward phase front curvature beats the diffraction outward phase front curvature. So it's not happening below the critical. Once you're above the critical and several times the critical power, you get this core forming in the center, and then you get white light emission in the central region. As far as why is the white light emitted, here is just showing you this. Basically, the frequency is related to the time derivative of phase, and the phase is just changing very, very rapidly in here because you're changing the index very, very rapidly because you're ionizing. So this causes a dominant blue shift, which causes this thing to have a white light look. There are limitations on filament usefulness. I had shown earlier, or I'd said earlier, that it's sufficient to have 100 femtosecond pulse and 1 millijoule for a filament. In fact, what happens if you send a joule 100 femtosecond pulse, it breaks up into about 1,000 filaments. That is 1 filament per critical power unit. Critical power unit, or critical energy unit for 100 femtosecond pulse is about 1 millijoule. So you get 1,000 of these filaments, and they're dancing around shot to shot because it's an instability, and the filament in the longitudinal direction in and out of the page here vary from shot to shot as well. So the control isn't great. The other issue is that, and these are measurements that we did in 2010, the filament electron density in this case was about 10 to the 16. So this is very, very low density. So the conductivity, if you want to have a conductivity, highly conductivity plasma wire to guide discharges, it's not very good. Plus, there are gaps in this effective wire, as we show here as well. So, in order to potentially find useful applications for filaments, and also just to understand more about filamentation itself, a number of questions occurred to us. First, like, what is the nature in detail of an optical nonlinearity that leads to the self-focusing? Self-focusing ultimately leads to filament formation. And what's the role of molecules? You know, that simple model I showed before was just an electron on a spring, but molecules are interesting. In fact, molecules turn out to be very interesting, as I'll show. The other issue is, you know, the atoms and molecules are actually sitting in this zone of transition from neutral to ionized. So they're sitting in a very high intensity region. The physics is non-perturbative. Is there some interesting behavior there? I'm not going to talk about it in detail. I mentioned it already. It turns out that the perturbative model still appears to be good in this non-perturbative region. And I'll leave it at that. If you're interested, there's papers in the bibliography that I can provide. Another question: how does the electromagnetic energy flow occur in a propagating filament? That is this thing really steady state, as the early picture sort of imagined for one of these things, or is there some kind of dynamics going on? And then finally, you are sending a fairly intense object through a medium, and it deposits energy in the medium. What is the effect on the medium after the filament leaves the building? Okay, so let's start with the optical nonlinearity. So again, we can start with an atom, and if the laser polarization is up here, so this is going to polarize the atom the following way, so that induces a dipole. And in air, you know, these single atoms are about the 1% level, and the rest of the air is nitrogen and oxygen, and what you'll get is basically an induced dipole that's torqued into alignment with the field. So you can see how that happens right here. So you induce dipoles on each atom of the molecule. The molecule is actually more polarizable along the bond axis than across it, and so that induces the torque. How do you measure that? So here's a random orientation of molecules. One measure of the orientation is the ensemble average of the angle between the molecular bond axis and the electric field. And for randomly oriented molecules, this ensemble average is 1/3. If you apply a field, though, there's going to be some alignment. So you're going to torque these things into alignment. And so this ensemble average number is no longer going to be a third. And in fact, the index change is basically proportional to the deviation from a third of this ensemble average of cosquared theta, which is basically the alignment. So we can measure this through the following thing. And this is one of the diagnostics I mentioned that we had lying around from our high intensity laser wake field work. This is called supercontinuum spectral interferometry. I won't get into the details except to say the following, that we have chirp pulses, and the chirp pulses basically mean that red is earlier in time than blue, and so there's a time evolution associated through this color evolution. And if you look on a spectrometer, you can then basically extract the time evolution by looking at the spectral evolution. And what you do is you perturb the spectrum of a second pulse with a pump pulse in a medium, and then interfere this reference with the probe, and you can extract from the spectral interferogram the transient behavior of whatever the pump did in this medium. And typically we use a flowing gas sheet, and we know the time dependence from that. We extract the phase dependence, and from the phase dependence we can extract the refractive index variation in time and in one spatial dimension with less than 10 femtosecond time resolution. Now, one of the things that we encountered in doing this was that it was important to have a flowing gas target, because if we did this in a static target, we would heat the gas. And the way we discovered that was that the density was lower than we thought for all the measurements that we were making. So somehow the laser, the pump, was causing the density to drop. This led us to a whole rich investigation that I'll talk about later. But this is an example of seeing something in an experiment, wondering what it means, and then following our noses to track it all down. So at this point, I'm just going to talk about the spectral interferometry. And in air, you see something pretty remarkable. So here's the pump pulse. It's moving to the left here in this picture at the speed of, at the group velocity in air. And it excites an alignment. And again, this thing on the left here is proportional to the index shift. So there's an index bump with all three. And then there's some revival that's happening here well after the pump is gone. And this just happens periodically. So for nitrogen, for instance, this peak is showing up around every 8 picoseconds or so. For oxygen, it shows up at about 10 picoseconds, every 10 picoseconds or so. And then in air, it's a mix. This is an index bump that's propagating behind the pump pulse at the speed of light, and it has a time and space dependence. So this is like a lens in air. It's an air index lens that's propagating behind the pump pulse, and it's beating at or appearing at a very regular interval. Why does this happen? Well, these are actually quantum echoes. This is quantum mechanics induced in air by a propagating intense pulse that's filamenting. So here are the molecular eigenstates. That's the total rotational angular momentum. That's the Z component of it. And the energies are just the rotational energies of a molecule. Again, we're taking the molecule as a rigid rotor. And in the end, what you've generated is a wave packet. When a short pulse hits a molecule, the molecule is excited into a superposition of rotational states. And this is what this is. And they're all phase locked with respect to each other because they are excited in a very, very short time. So the intense pulse locks the relative phases of these things together. The analogy to this is basically a bunch of springs. You can think of each one of these springs as being a different rotational state in a molecule. And at t equal to 0, when the short pulse hits, you pull all the strings at once, then you watch them respond. And eventually, at some characteristic beat frequency, they all come back at the same time. So, for example, in nitrogen, this time is about 8.3 picoseconds, and that's what I showed in the previous plot. So here is an actual measurement of the, so it's a little longer than 8.3, it's 8.5-ish, but this is the evolution of one of the revival echoes, the first one in pure nitrogen. And it's got nitrogen and it's got a contribution from oxygen here as well. So this is the time evolution of a molecular index variation in air. And this is an experiment that probes this. So the pump is exciting the molecules in this spatial dimension. This is a transverse spatial dimension. The pump is exciting it here. And then we just delay the probe as a function of time with respect to this structure. And you can see that the structure has a massive effect. It actually steers the probe into position, into a focusing position. This is a focusing position. This is defocusing. So it actually expels the probe from the beam, refocuses here, then it expels here, and so on. So in other words, you can control beam propagation in air at STP using quantum mechanics. The paper is down here if you're interested, from quite a long time ago. So next, what is going on in just regular garden variety filamentation? Those 100 femtosecond pulses that people were using from 1995 on, what are they actually doing in filamentation? Well, air is mostly molecular, and so let's look at the molecular response. Now, I spoke about the quantum mechanical response, and we analyzed in the last slide what happens when we probe with a probe around one of the revivals, around 8 picoseconds. But what happens around t equals 0, right with the main pulse that's torquing these molecules? Well, in argon, this is the change in index induced by a short pulse. It's just one peak. So because the response is essentially instantaneous, here's transverse position, here's time, it's just one peak. And basically when you're probing perpendicular and parallel to the pump, there's just a difference in size of the response. But when you go to a molecule, you have this effect. You have this prompt response, and then you have this delayed response. When you go to a perpendicular probe, it's more or less the same thing. It's just a little less intense. So this is the electronic response. This is, and I'll show a picture of this in a second, and this is the rotational response. You can plot all of these things out here. And in fact, let me just go back to the previous slide. Yeah, so the prompt response is just this. It's the immediate polarization, and the rotation response is the torquing alignment. So that we're seeing that in one shot here. So here's the prompt response, the electronic response, and here's where it rotates into alignment. Okay, so what does this mean for air filamentation? So we did this experiment and we varied the pump pulse length. And you can see you have to be less than about 80 femtoseconds or so to see this prompt response. So this is the electronic response, and then the molecule decides, the sluggish molecule decides to rotate. Now the response goes up here. When you're at 100 femtoseconds, which was the pulse length for many years in the filamentation community, it's almost all rotational. So the index of refraction that they were measuring or thinking or modeling wasn't strictly correct. They needed to take into account the rotation of the molecules into alignment to understand the filamentation completely. So here's a model that matches it pretty well, and it just breaks the thing up into two pieces. Here's the instantaneous response, which gives that spike, and here is the delayed rotational response, which just gives this this second peak. And at long pulses, this is pretty much the dominant piece. Okay, what happens after the filamentation passes through the gas? So here's the filament coming from top to bottom. And this gets us back to the question that was asked when we were doing the measurements of gas response. Remember, I said we had to have a flowing target because the laser heated the gas. Well, now we're in investigation. Well, what is going on? So here's a filament going through the gas, and on the time scale of an acoustic wave in a gas, a femtosecond filament is really like a delta function. It deposits all of its energy almost instantaneously. That energy thermalizes and it launches a single cycle acoustic wave into the ambient gas. So basically what's going on is the following. On the right-hand side is what's going on in the filament. So there's two energy terms. There's basically the energy due to the plasma that the filament generates, but then you're also exciting molecular rotations because it's air. And both of those things thermalize. In this case, in terms of the plasma recombines. In terms of the rotations, you are decohering the wave packet. And in the end, what you get is a thermally repartitioned energy to the neutral gas. And if we just take it as an ideal gas, it's just NKT. So this is the temperature of the neutral gas after repartitioning, and this is the density. And this is basically the delta function pressure profile. It's delta function in time, not in space, because the energy is essentially deposited instantaneously, and that drives air hydrodynamics. How do you measure it? Don't get blinded by all this detail here. It's just a spatial interferometer. So we just go longitudinally through a filament, and we just basically look at the evolution of the index of refraction, and the index of refraction of the neutral gas is related to the density of the gas. And it is neutral gas because when we do this, the gas is long since recombined and thermalized. There's no longer any evidence that a filament was there except for a single cycle wave that's blasting outward radially in the neutral gas. And so these are the kinds of pictures that we can get from the interferometric experiments. So here's early in time, 20 nanoseconds after the filament. It's recombined a long time before that, but the air hydro effects are still there. And so as you wait longer and longer, this acoustic wave is propagating out radially. By a couple of microseconds, it's gone. And all that's left here is a density depression, which we call a density hole. And this thing lasts, at least in this experiment, for 100 microseconds or so. For larger filaments, it can last as long as milliseconds. And I'll talk about that. It's easy to simulate using an in-house hydrocode, and the agreement is very nice. Okay, so that raises the question, at least it raised the question to us. Maybe it's not obvious to you guys, but it was obvious to us at the time that, well, if we're doing this kind of long-lived air perturbation, this density perturbation in air, can we somehow make a waveguide out of it? Well, it took us about 5 minutes to understand that this did not conform to an optical fiber, right? The optical fiber, the core index has got to be greater than the cladding index. And this thing I showed you on the previous slide, this is just a density hole. So that the index in the center is lower than the index in the outside. So this is not a guide, it's in fact an anti-guide. But then that said, well, what if we have 4 of these things? The index in here, the ambient air, the unperturbed air, is greater than any of these 4. So can we guide in the center? Why? Then you say, well, why are air waveguides of interest anyway? Why even bother with this? Well, some of the things that occurred to us at the time, you could use it to control beam positioning, pointing. Maybe you could use it to do remote signal collection. And then the thing that really appealed to us, wow, you could potentially do high average power guiding because the filaments themselves are not high average power. But if the filaments could enable a structure in air that could guide high average power, that is very cool. So the first thing, the remote signal collection we demonstrated. We actually made a discharge with a laser breakdown, essentially a laser breakdown discharge at one end of the of an air waveguide. And we collected, I haven't shown the air waveguide result, but this basically, I'll do that in a minute. But this shows that we collected a spectrum at a higher intensity than we would have just letting it, inverse square law spread to our detector. High average power guiding. Well, in a fiber, you have the standard bulk damage threshold scattering losses. In air, the main issue is for high average power is thermal blooming. Here's a paper that discusses thermal blooming. Our papers in both 2014, I'll talk about, in 2023, do an analysis that shows that you could potentially support megawatt class lasers in these fibers, and mainly because the absorption, while not zero, is still not big enough to defeat the index changes that we can impose in an air waveguide. So the simplest experiment that we started with was the four density holes. And the way we made the 4 density hole filament, we just generated a TEM1 beam. It's amusing how we did it. You can read about it in this paper if you're interested. It was a real a really messy thing, sort of a fun, messy thing that we did. But the bottom line is we got this kind of a pattern in the laser focus. And this made 4 filaments that were parallel to each other, and each filament left one of these density holes or a reduction in density, and then we guided. So the probe injection came from the other side, and it was injected into this air waveguide. So first, this is the evolution of the 4 density holes. This movie is just running continuously. So at the beginning, you can see 4 holes there. There it goes, and then it expands. These 4 single cycle waves are seen to sort of move out radially. And then for a period there, you have these 4 holes. And this thing in the middle is the cladding. There it is, that blue thing. That's the core. And then the blue stuff on the outside is the cladding. And here's some single frames from this movie. You can get a time scale for the life of this thing. It's fairly straightforward. This thing is limited by thermal diffusion in air. That's what, once you deposit the heat and the hydro starts evolving and the acoustic wave is left, all that's left is this object that dissipates through thermal diffusion. So its time scale for dissipation is just the size or the radius squared divided by the thermal diffusivity. If the structure is of order 100 microns, the thing dissipates in half a millisecond. If the structure is order a millimeter, the thing dissipates in 50 milliseconds. So these are really, really long time scales, way beyond anything that you could have imagined when you were back thinking about the femtosecond interaction. The femtosecond interaction is very, very interesting, but what it leaves behind and the time scales of what it leaves behind are very interesting as well. So here, just look at what's inside this dotted ellipse here. These are guided modes as a function of time. So this is a roughly 1 meter long, it's really 70 centimeter long waveguide. And as we delay the injected pulse, which was a green 7 nanosecond Q switch pulse into the air waveguide, there's a variation in guided mode. So this thing works. And then at the time, Eric, who was a student, said, I'm just going to run a real-time movie here. And so this is a waveguide generating at 10 hertz, and the probe is also running at 10 hertz. And he was basically rastering the probe, the green probe, up and down and left and right through the waveguide. So you can see it's a pretty crummy looking Q switch pulse, but when you go through the waveguide, it's trapped and it has a nice move. So this thing really works. Then we decided we want to try this over 50 meters. It took a few years. We got diverted by other stuff. The other stuff that we got diverted by, I'll talk about shortly. But we basically got through this set of experiments using donut modes. And a donut mode filaments, here's the donut mode, and it filaments into a ring of filaments. Here we go. And how do you measure a ring of filaments in the middle of a beam? Well, you use what we call a helium cell imager, and I'll talk about that in a minute. So this allows us to actually image the collapse of a donut mode into a ring and then the generation of a bunch of filaments. And this ring of filaments forms the cladding of a waveguide. And it can do so if this is a diameter that's big enough, over 50 meters. Here's a simulation that shows once you've demonstrated this multi-filamentation around a ring, then long after the filaments are gone, you have thermal diffusion that forms a very nice cladding. And so this is the cladding and this is the core. So this is the 50-meter hallway experiment, and this experiment had Tony Valenzuela and Aaron Schweinsberg and Eric Rosenthal joining us. Andrew Goffin is the student. So we used an LG mode with over 100 millijoules, 300 femtoseconds, and the ring diameter was less than 6 millimeters. And we just sent it down a long hallway, and then we sent a green pulse through this thing. If you want to read about this, it was published earlier this year. And so this is just a measurement as a function of distance down the hallway without the waveguide there. This is the beam. With the waveguide there, this is the beam. So there's clear guiding. The efficiency isn't great. It's only less than 20%. Why is that? It's because the coverage of those filaments around the circumference of the waveguide is not that great. We've got to improve that, but we know how to improve it. The really intriguing part of this was we then sent a CW beam down this waveguide to see what the time evolution was. Here it is here. And you can see that the waveguide itself has a lifetime of several tens of milliseconds. This is consistent with the millimeter scale of the waveguide. So this really conforms nicely to the thermal diffusion picture of how these waveguides dissipate. So then the question is, well, if they dissipate over a few milliseconds, can you send a kilohertz laser in to refurbish, re-up the waveguide so that it never dissipates? And so that's what we did here. And this is a paper, if you're interested, it was published earlier this year in Optica. So this is a kilohertz laser. We're not going to go down 50 meters anymore because we don't have that much energy in our beam, just a few millijoules, 5 millijoules. And this is basically showing, this is how we adjust our rep rate. We just use a chopper. So the thing's always running at a kilohertz. So the lasers operate in the same way. And we use choppers. And we change the rep rate, and over a slightly less than a meter distance, we basically make, again, one of these quad waveguides, and we guide a beam. And we show here that we can achieve quasi-steady state operation if we're generating the waveguide in this range between above 250 hertz. So once we're above 250 hertz, you can see here that the waveguide is more or less steady state, and you just see the sawtooth ripple at the top. So this is guided intensity, or guided energy as a function of time, and it's a CW beam. So there's a CW beam going in. For the low rep rates, it just declines, and these are basically the thermal diffusion timescales. We also looked at the burst mode, and the burst mode shows these things onset very, very quickly. Guided beams improve in efficiency with rep rate, and that's what this slide shows essentially. So you can just see this here. This is basically the delay of the beam between pulses at a kilohertz. Okay, so now this is the weird section, and I'm going to go pretty quickly through it. This goes back to the quad filament that we used to make the waveguide. One of the things we noticed, this is a side view of just a double filament, that these things are locked in phase even after filamentation. Now, you know, I had said earlier that there is tremendous phase shifts going on in the filament. That's how you get white light generation. Nevertheless, you still have phase locking between these two. That's why you have this null in the middle. Like, how does that happen? And so that's why we developed this helium cell imager. So we basically want to see what the phase and amplitude is in the middle of a filament. And so the idea was you send a filament through air, and then you terminate the air at a helium-air interface. Helium is much less nonlinear than air. So basically, nonlinear propagation terminates, and then you get linear propagation, and you can do imaging of this interface. And this is described in this paper from 2016. An earlier version of this scheme was developed by Tony Ting et al. At NRL. in 2005. This only did intensity. We souped this thing up by measuring intensity and phase. So the way it works is a femtosecond air filament goes into this nozzle, and then the nonlinear propagation stops. This is all helium. Helium is actually slowly flowing out of that nozzle. Helium all the way back here, and then we image the beam into an interferometer so we can get intensity and phase. What did this thing measure in the middle of a filament? This is sort of cool. Pre-collapse, this is just the beam, the intensity and the phase, nothing special. But after the beam collapsed, we saw these kinds of images. This would jump from here to here, from shot to shot. There would always be a 2 pi phase difference between this and this. These are phases. And the intensity would always show this pattern. There would be a ring with intensity in the middle and intensity outside, but this is a null. So this is the kind of picture we would always get. What is that? And that led us to a simulation. Here's a simulation. It's described in this paper again at the bottom. The pulse is propagating from right to left. And this is the laser pulse. This is a phase picture. I'm going to stop it right here. This is a phase circulation here and here. This is actually a quarter slice out of the beam. And here's the intensity. Let me continue it. I won't get into this. These are basically toroidal vortices that develop in the middle of the beam. It's hard to visualize it unless you've seen this movie a lot of times. If you go to this paper, there's links to these movies. But basically, there's a toroidal vortex here. And I've drawn it, the propagation the other way. But this is phase picture. There's a vortex here, and there's a couple of vortices here. They're all described. This is the null, and this is the propagating pulse. So this is a simulation. What is this? Well, I don't want to. Let me skip this. This is described in the paper, and I'm quickly running out of time. But this explains why a vortex forms. Let me just say very quickly that if you look at the inside of the beam and the outside of the beam, this is where the most intense part of the beam is in a filament, and this is the less intense part. Because you have so much phase shifting on the inside with respect to the outside, you quickly develop what's called a phase dislocation. And that phase dislocation gives rise to vortices of opposite sign, and they launch. This goes forward and this goes backwards. These are the vortices that we call spatio-temporal optical vortices. Another way to view this is that as the beam collapses, this is the log of intensity, as the beam collapses, gets more and more intense in the center, the phase shift in the center is much bigger than the outside, and this is the place where you have phase dislocation. And phase dislocation means the phase adds up. There's a pi phase dislocation, so the field is a null right at that location. I want to summarize our filament experiments and phase measurements with this picture. What is going on in a propagating filament is this. Here's the so-called light bullet that's going through and filamenting. The front of the pulse has energy flow going in. This is in the frame of the pulse. Obviously, a pulse itself isn't just doing this. The pulse is moving to the right. But in the frame of the pulse, there's a component of energy going inward. This is due to the self-focusing. And then later, there's a component of the energy going outward. This is the defocusing from the plasma. These two things meet at a very sharp interface, and that sharp interface is where the vortex sits, and the phase circulates around around this way. And this happens all the way around the pulse. So filamentation is actually governed. The energy flow in a filament, in a filamenting pulse, is governed by this vortex. Left to right here is the time domain, up and down is the space domain. So this is a filamenting pulse right here. There's this vortex surrounding this pulse, and the ring null is basically what we saw, and the phase jump of 2 pi across the plane here is basically looking front and back of this ring. I am going to skip through all of this right now. This is a regular vortex. Let me skip because I know I'm going very, very slow, not quickly enough. But that vortex in a filament is caused by what we call spatio-temporal phase shear. So the idea then was to impose spatio-spectral phase shear. And there's this device out there called a pulse shaper, which allows you to do that. So what you do with a pulse shaper is you shape a pulse in the spectral domain. The way you do that is you go off a grating, which spreads things spatially. You collimate with a lens, and then you put some kind of a phase match or a phase mask or a spatial light modulator here. And that does something in the Fourier domain or the spectral domain. Then you undo the process by going off the second grating. And so we have developed phase masks that generate this kind of an object. This we call an edge-first rolling donut. Normally, donuts in optics go the other way. So if you project the donut on a wall, it looks like a donut. If you project this on a wall, it won't look like a donut. It'll just look like a beam. The hole is actually going the other way. And there's angular momentum going around in this, angular momentum is pointing sideways, and there's phase circulation going around that axis. So this is the object. We call this a spatio-temporal optical vortex stove discovered in a filament. Well, how do we measure them in flight? We generate these things. How do you measure them? Well, you've got to develop an object, a device that actually measures phase and amplitude with femtosecond resolution in space-time. I won't get into the details here. It's in this paper. Again, it's in our bibliography. If you need to if you're interested, read it. But these are the things we measure. So basically, just let's focus on these two central columns. This is the pulse donut. This is the edge-first rolling donut, and it's propagating from right to left. And this is the phase. So this is space and time. This is a forked phase pattern, but it's in space-time. And this basically is characteristic of a phase evolution that is circulating around the axis, and you see it right here. Here's a phase map. We demonstrated that these things can be the source of second harmonic generation. So we basically put a BBO crystal after this, and we generated a pulse at 400. This is 800 nanometers. We can generate at 400 nanometers. Because second harmonic generation is fundamentally a quantum mechanical process, the conservation of angular momentum in this process tells us that sideways pointing orbital angular momentum is a characteristic of single photons. This is a fundamental statement which we were led to by following our nose in our filamentation experiments. We've also developed a mode theory of spatio-temporal optical vortices. I'm going to skip through this. Here's the reference. The mode theory has been verified by experiment, again in this paper. So here's the theory. Here is here's the experiment, and here's the propagation with respect to the beam waist. Finally, you can calculate the angular momentum of these spatio-temporal optical vortices. And the interesting thing, there's two things that came out of our theory, and we are now doing experiments to verify these. One is that the OAM, or orbital angular momentum, is half integer right here. There's actually a bit of a controversy about this in the orbital angular momentum field. This was a pre-existing field, and that when we got involved in it, once we started doing this spatio-temporal optical vortex stuff. So we showed that you could actually have half integer orbital angular momentum. The other part of this is that there's some material dependence here. This is inside a medium, and this led us to speculate that, or posit that there is a quasi-particle in dispersive medium, which has quantized orbital angular momentum, and we call this thing a stove polariton. And we're doing experiments right now to verify that this thing exists. So with that, not too bad. Let me summarize, not technical summary, but just sort of maybe a summary of sort of the points I've been trying to make qualitative points I've been trying to make. Filament physics is really interdisciplinary, and it's very, very rich. And and I think I've shown that all the things we've done have encompassed all these topical areas. There are applications currently under development in our lab, especially with air waveguides. We're working on those, and on spatio-temporal optical vortices. And then, as I kept saying during the talk, there's lots and lots of publications over the years in these areas. I counted up about 40 to 45, and I have a bibliography that I can distribute upon request. Thank you.
Thank you, Howard. I really appreciated the talk. It was very interesting, and I think I learned quite a bit. We do have, we'll ask just one question from early in the talk, and if more questions come in, we will forward those to you. Early on, when you were introducing the idea of filaments and supercontinuum generation, there was a question about the integrity of the beam retaining its integrity even as you're doing this process, and so if you could elaborate on that, maybe in the context also of now even maintaining the orbital angular momentum, and then they ask about doing this in the condensed phase.
So is this? So by the integrity, you mean the preservation of the phase relationships among the filaments, that part of it, or?
It was even before that. I think they were just talking about, well, we could ask the speaker, Nicholas Ball, if he would like to elaborate.
I mean, I think you mentioned it was in the context of supercontinuum generation. So I guess the answer is that, if I understood the question, that if you run not too far above the critical power for self-focusing, you will be in the single filament regime all the time. So for supercontinuum generation, if you keep your beam, not too many critical powers, it'll stay single filament and it'll be very stable shot to shot. Okay. So stability is, but once you're 10 peak critical or more, let's say, then the filaments start jumping around and it becomes unstable, because then you become sensitive to not irregularities in the beam. Those little irregularities can seed filaments.
Thank you. That particular guest has departed, and we have reached our time, but I just want to also thank you so much for the brief and the talk that you gave. And again, to remind the folks that it is recorded and it will be published on our YouTube page once it has reached a public release process. So thank you all. And at this time, I will have everybody depart from our webinar. So thank you so much and have a great night. Any closing words, Dr. Roach?
No, I want to ask Howard about the angular momentum quantum number L and halving that, and trying to understand how the relationship to total angular momentum quantum mechanically, and I'd love to, at a time over a cold beer to discuss that with you. Over.
Yeah, that's a fun debate. The interesting sociology is that we're mixing it up with some European theorists, and they're getting very. Is anyone else still on the call?
Yes, yes, there are. So we will need to depart and save those conversations for later. Thank you, gentlemen. Have a great day.
All right.